Welcome to Calculus. We conquer our fears and flex in the face of adversity. On this episode, Stevenson will demonstrate I want to show you now how we can use implicit differentiation, but this time with a point, because I talked about that in a previous video about how you need to use an ordered pair in order to find the numerical derivative. So let's look at this example. This example says find the slope of the curve, of the circle, x squared plus y squared equals 25 at the point 3, negative 4. Now, even if it didn't tell me it was a circle, I would know it's a circle because both x and y are squared as a sum. And also 25 is a nice, square. This doesn't have to be a perfect square, but I can tell by the structure of this equation, it's a circle. So the first thing we need to do is figure out the derivative because it's asking for the slope, right? But because this is an implicit function, I have to do implicit differentiation. So I'm going to do the derivative of each individual term. Now, notice this is my only y term, so I'm only going to generate one dy dx here. So what I'm going to do now is I'm going to apply what I know with derivatives in terms of constant rules, power rules, and so forth, chain rules, and then when I go to do the derivative of y squared, it's going to generate a dy dx because it's an implicit function. It has that hidden function. So I need to know what that hidden function's derivative is. Now from here, I want to isolate dy dx because that'll give me my slope. So I'm going to subtract 2 to the right, and then I'm going to divide by 2y. So this expression will give me my slope anywhere I want on my given circle. All I have to know is the x and y coordinates. My x and y coordinate are my specific points given here. So I'm going to evaluate dy dx at the point 3, negative 4. So notice my notation here. So this is saying take this derivative, which is really this expression, and evaluate it here. So this is the slope at the point 3, negative 4 on this given circle.